need to plug me in here?
Nope.
Like we did the other day, okay.
No, it's all good.
But it works, it does work on that.
My laptop just like, so, it doesn't have any hard left.
Yeah, that was very.
The floor is right there.
We'll just hear that.
But I didn't know what question.
Yeah. Yeah.
Wait, so you're also still, like you're still
Okay, I think we have close to a quorum here. Before we get started on scattering, next Thursday we'll be doing starting hydrolite labs in the afternoon. But the fellow who now is in charge of hydrolite is going to be off the grid next week. So he wanted to make sure we get it installed this week in case something weird blows up. He'll have a day or two to fix it. So if you go to the useful codes directory that you guys have access to, I put 3 files there. If you're running a Windows computer, just download this file called install student HE60 Windows 32, and that's an executable. Install it. You'll probably have to persuade the computer that it's okay to trust me and all those kinds of things. And click on that. It should install the code. If you're running an Apple computer, there's an install student HE6 for OS 10 zip file, and then there's a separate set of notes on installing on Apple computers. So you guys download these 2 files, follow the directions there, and install it on your Apple computer. And then, you know, sometime this evening or something, we can have a couple of people do some test runs and just make sure it all works okay. It's been working for, 20 years, but there's always a chance that something got screwed up when he created these files, and it'll say, license expired or some weird thing like that. So anyway, before you get to have dessert at dinner tonight, you need to do this and let me know if there's any problems. Okay, so if this thing works now, it's going to the next slide here, but it's not showing it up there. So what's going on here? Let's start over with slideshow from the beginning. I have no idea. Well, no, see, I'm advancing here. Okay, now it's decided to work there. Let's try another one. Okay, well, okay, it just seems to be extremely slow. I made the stupid mistake of doing this massive upgrade before I came to the class to make sure I had all the latest virus things and software and all this. And of course, now nothing works like it used to, but live and learn. Okay, so today we're going to talk about mostly the volume scattering function, but also we're going to review a few of the basics of scattering, which Colin talked about the other day. Then we'll talk in more detail about the volume scattering function. We'll look at some data for scattering, both volume scattering functions and scattering coefficients, and backscattering coefficients, and so forth. And then we'll take all these pieces and screw them together and make some bio-optical models where you can do things like plug in chlorophyll and get back absorption and scattering. And those models you'll then see used in hydrolite next week. So that's where we're going. Now, you recall this little organization chart I showed the first day. You've been learning about absorption coefficients and beam attenuation. Today, we're going to start with the volume scattering function, from which you can derive the scattering and backscatter and other things that are of interest. So this lecture now kind of finishes off this box on inherent optical properties. And the inherent optical properties, or IOPs, are things which depend on the concentration, size distribution, compositions of the particle, or dissolved substances, and of course, water itself. They do not depend on the light field that's in the water. So you can take a sample of water, take it in the laboratory, and measure absorption and scattering. And it has nothing to do with sunlight that was on the ocean. In a few days, we'll learn about apparent optical properties, which have to be measured in situ because they depend on the ambient light field. Anyway, the two fundamental IOPs are the absorption coefficient and the volume scattering function. And if you measure those things, then anything below here can be derived from those two things. Okay, so why is scattering important? Well, here's approaching Annapurna South Base Camp in Nepal, almost 14,000 feet. It's a great trip you guys need to do. We'll talk more about it later. But there was this spectacular halo here. And everything you see in here, except the sun itself, is due to scattering. So the halo is scattering of sunlight off of ice crystals in the atmosphere. The blue sky is scattering of sunlight off of nitrogen and oxygen molecules. The snow and the rocks that you see here, that's sunlight that's been scattered or reflected off of the surface. And so there's what you see. Now, what would the world look like without scattering for this scene? What would you see? All you would see is the sun itself coming through unscattered and not as bright as it was because there was some absorption along the way. So I think that pretty well says why scattering is important. There's other reasons. Well, it determines the angular distribution of the radiance, and we just saw this radiance distribution here of the picture, and yeah, all of those light coming from all these different directions was determined by scattering. It's the basis for ocean color remote sensing. If you didn't have scattering to get the sunlight that gets into the water back out of the water, no remote sensing. It enhances absorption effects. There's an old saying that if you have a lot of scattering, a little bit of absorption goes a long ways, because if the light's just scattering around, there's a lot of chances for it to get absorbed by something. If the light just goes straight through with very little scattering, then there's less chance that the light will be absorbed. It degrades visibility. So when you look across at the mountains under something and it's kind of hazy or, not quite clear, that's usually because of scattering in the atmosphere, not absorption. It's a diagnostic for particle properties because scattering depends on things like the size and the shape and the composition of the particles, which can be a problem, but it also means that if you measure scattering, maybe you can learn something about those things because they're very connected. And in my opinion, scattering has lots of mathematics, so that makes it a lot of fun. Okay, scattering simply means that the light changes directions and maybe wavelength. So it occurs in various places in the ocean. It occurs at the sea surface when light is reflected or refracted by the water surface itself. It occurs within the water body when it's scattered by water molecules or phytoplankton, mineral particles, bubbles, whatever. Scattering occurs at the bottom of the ocean when light is reflected by sediments or seagrass or coral. So any of these processes are all scattering. I'm only going to talk about scattering within the water here today. Later, we'll have some lectures on what happens at the surface and how light is reflected by things that might be on the bottom or in the water. As Colin mentioned, keep in mind that all scattering is basically the same. It's caused by a change in the index of refraction. So Colin showed a figure like this where we have, let's say, air and water, and the light is coming along. There's one index of refraction here, and there's a different one here, and that causes the light to be both reflected and to change directions if it's transmitted. So that's reflection in water at an air-water surface due to the fact that air and water have different indices of refraction. If you have a particle in the water, well, the water has one index of refraction, the particle has some different one. Then the light waves coming along here, if this is a regular particle with a higher index of refraction than the water, then the waves will tend to slow down. That bends the wave fronts, and the light now goes off in other directions. So that's kind of the wave viewpoint, or the ray viewpoint would be the light would come in, be refracted, or be scattered off the surface. If this particle has the same index of refraction as the surrounding water, what happens? It becomes invisible. There's no scattering. So you just, the light just goes right through it and never knows the particle is there. Again.
When you say invisible, do you mean like truly like invisible, or it just doesn't change the wavelength properties?
Well, the light will not be either reflected or refracted by this particle if the two indices of refraction are the same. And technically, I just have to say the complex index because there's both an absorption part and a real part. But yeah, the light just doesn't see the particle. It's not affected by it because it's going to be, these wave fronts are going to be seeing the same index of refraction. So it's just like the particle's not even there. Here's scattering by turbulence in an underwater vent. So here's cold water, and it has some index of refraction. Here's an underwater thermal vent spewing out this really, really hot water. And the index of refraction has changed because it also depends on temperature as well as salinity. So you see, you don't see as well through the hot water plume as you do through the cold water because they're scattering by the change of the index of refraction in that hot water. So there's lots of ways that you can cause scattering, but they're all really due to a change in the index of refraction. And as Colin mentioned, these terms like Rayleigh scattering or me scattering, they're not different physical processes. They're different mathematical models that describe scattering in certain regions. And the regions are determined by the ratio of the particle size to the wavelength and by the index of refraction of the particle relative to that of the surrounding medium. So Rayleigh scattering, for example, is a mathematical model that describes scattering if the particle size is much, much smaller than the wavelength. Me scattering works for any particle size and any index of refraction, but the particles have to be homogeneous spheres, and so on. Okay, so you kind of recall from the lab on Monday playing with light that if you shine an incident beam into the water and there's stuff in the water, well, the light scatters off, and if you're looking at it from the side, you see light going in different directions, and there's a polar scattering angle psi, or if you look into the beam, which of course you shouldn't quite do, but play like it's a flashlight, then the scattering also goes off in different azimuthal directions, and there's an azimuthal scattering angle alpha. In general, if you have irregularly shaped particles, which you usually do, but they're randomly oriented, or if you have spherical particles, and if the light's unpolarized in both cases, then the scattering will be azimuthally symmetric. So it's only the polar angle that matters. Now, if you have non-spherical particles and they're not randomly oriented, or if you're shining a laser light through the water, even if the particles are spherical, then there will also be an azimuthal dependence. And that's the case with anytime you shine like this laser, which is inherently polarized through the fish tank. And if you look down at the top of the fish tank and you rotated the laser, you saw that what was coming out at 90 degrees was bright in some cases and dim in some cases. So that's an azimuthal dependence. Okay, so this volume scattering function, this is kind of what you see in the laboratory. Psi equals 0 is always the direction the light's traveling, or that's forward scattering. And then psi around to 180 degrees for pi is light that gets scattered backwards, so backscatter. So if you plotted this on a polar diagram, you'd see something like this. And if we just take this curve here and just sort of unwrap it and plot it from 0 to 180 degrees, then that's our volume scattering function, as we'll define in just a minute. But that's all that's going on. This is the way you almost always see it, but sometimes people will plot it like that. Okay, Colin mentioned solid angles versus plane angles. The definition of a plane angle simply says, take a circle of some radius, you have an arc length out here, L, you divide that by the radius, and that gives you the plane angle theta here. Units, it's really a non-dimensional number, but we call it units of radians just to remind ourselves that we're talking about angles, not something else. With solid angle, you simply have a sphere now, some radius r, and there's a little patch of surface on the sphere here. And so you take the area of that patch and you divide it by the radius squared, because this has units of distance squared divided by distance squared. And that ratio is simply the definition of solid angle. So it's area over radius squared, it's capital omega's the standard term. Now over here, there's 2 pi r is the radius of a circle. So if I have a whole circle, L is 2 pi times the radius divided by the radius. So a circle has 2 pi radians. Here, the area of a sphere is 4 pi times the radius squared. So you divide by radius squared. A whole sphere has 4 pi steradians, and ster comes from Greek. It means solid. So basically this solid angle. So 4 pi steradians in a sphere, and Colin showed you that the differential element of solid angle is sine psi, d psi, d alpha. If it's azimuthally symmetric, you can use 2 pi sine psi, d psi. And we'll look at that again next week. We did get a little question on which angles to use. My convention on angles is I'm going to pick a coordinate system, x, y, z, that's whatever's convenient for my problem. And then I always use primed variables for incident or unscattered light. And I'm going to use theta and phi as being angles, polar and azimuthal, in my fixed coordinate system. So if I have a ray coming along here, light's going in this direction, the red arrow, it's going in direction theta prime, phi prime, and then here it interacts with the particle and it goes off in some new direction where in the XYZ system, that would be theta and phi. And I always use unprimed variables for the scattered or final direction. And then theta always refers to polar angle in the coordinate system, but the polar angle relative to the direction the light was going initially and then scattered, that's the scattering angle psi. And that's just the way I've been doing things for decades. Yeah, Colin.
So then what was alpha in your previous slides?
I didn't put it on here. In this case, phi is in this coordinate system. You usually, when you're doing polarization, you have to use a local coordinate system where you think of like a z-axis going in the direction of the light, and then you have to come up with some xy coordinates, and the alpha is in those coordinate systems. And those are, we'll see that maybe, I hope Ken Voss talks about it, but the psi is polar angle in a coordinate system that has z going in the c prime direction and alpha are an x prime and a y prime at right angles to this axis, not at right angles to this axis. So I didn't have that on this figure, but we're not going to deal with the math of polarization in this class, but it gets really nasty keeping track of all of these coordinate systems. And enough said there. But so my alpha is not the phi here. It would be a phi that's in a coordinate system that's not shown here. Okay, so how do you actually define the volume scattering function? Well, here we've got a little volume of water and it's some thickness delta R. There's a little area delta A here shown in bluish. And so delta A times delta R is the volume delta V. We shine some light onto this surface here. That has some power phi, so that's watts or watts per nanometer if it's spectral power. And inside that volume, some of the light will get absorbed, some will get transmitted through, and some will be scattered off into some direction. And we'll measure that, how much light goes into some little solid angle. And I've drawn this little red ring here. If we assume azimuthal scattering, then all the angles in this red ring all have the same polar scattering angle. So they get counted the same. So Howard Gordon in his work uses the notation delta squared for phi s to remind himself that this is a second order small quantity. It's small because delta R is small, and it's small some more because the little solid angle element is small. Whereas the transmitted or the absorbed light are small just because delta R is small. So it doesn't really mean squared. That's just his notation. And if it's good enough for Howard Gordon, it's good enough for me. So anyway, we make these measurements of how much power goes into here. We know how much power went onto the air to the little volume here. We know delta R, we know delta omega. So if we take this ratio of scattered power normalized by incident and divided by the distance and by the little element of solid angle, and then we think conceptually of taking the limits as delta R and this delta omega go to zero. That's the mathematical definition of the volume scattering function. And you think if you take the limits, you'll sometimes see it written as the second derivative of the scattered power normalized with respect to R and with respect to omega. Okay, so there's something called intensity, which we haven't defined yet, but intensity is power scattered by a little point source or a little volume per solid angle. You know, we've learned about irradiances, which is light per unit area. Well, intensity is how much power there is per unit solid angle. So if we look at this equation, well, here's scattered power divided by solid angle. That has units of intensity. And irradiance is the irradiance onto this area here is the incident irradiance divided by the incident power divided by the area. So that's the incident irradiance. And the volume is just delta A times delta R. So we can rewrite this as the scattered intensity normalized by the incident irradiance onto the volume divided by the volume. So that's where the name volume scattering function comes from. And of course, all of this stuff, it's on the web book, it's on the ocean optics book, it's in light and water, et cetera. So you don't have to worry about remembering all of this. Okay, as I've said, the volume scattering function tells you everything you need to know about scattering by unpolarized light. If you're doing polarized light, there's actually a 4x4 matrix, and the 1,1 element of the matrix tells you how unpolarized light scatters into unpolarized light. That's the VSF. The other 15 elements tell you things like how does vertically linear scatter into horizontally linear, how does left circular scatter into right circular, and so on. More on that next week or when Ken gets here. So if we have the volume scattering function, you just integrate over all solid angle to get the total amount of scattering without regard to what direction it was scattered in. That's the scattering coefficient. So conceptually, this is a definition, integrate overall solid angle. How you do that is you need to know the volume scattering function as a function of psi and alpha, and then you can integrate over directions polar angle psi, azimuthal angle alpha. For azimuthally isotropic scattering, as Colin showed you, the d alpha integral just becomes 2 pi, and you see this guy. So there's how you get the scattering coefficient from the volume scattering function. And this guy, of course, is beam attenuation minus absorption. Likewise, if you want the backscattering coefficient, you just integrate from 90 degrees to 180 or pi over 2 to pi. Same equation, different limits on the integration. There's something that's very useful called the backscatter fraction. That's the ratio of the backscatter coefficient to the total coefficient. Typically in the ocean, that's a number. For phytoplankton, it might be 0.5%. For mineral particles, it might be 3 or 4%, but it's in that few percent range are typical backscatter fraction values. And this is very important because the light that gets scattered back out of the ocean to do remote sensing really depends on what percentage of the light that's heading downward from the sun gets backscattered upward. So you're going to see this guy for the rest of your life. And some people call it B sub B tilde, tilde meaning a non-dimensional thing in this case, or some people call it capital B. There was never a worse notation invented than using B sub B for backscatter coefficient, because the big B means scattering and the little b means backward. And I didn't invent it, but that's the way it is. Okay, there's another thing called the albedo of single scattering, is the total scattering coefficient over beam attenuation or absorption plus total scattering. That's often called the probability of photon survival, because if a photon interacts with a particle, it can be either absorbed or scattered. If there's no scattering, B is 0, omega naught is 0, and the photon is not going to be scattered. If there's no absorption, A, then B over B becomes 1, and it's guaranteed to be scattered. So if omega is 0, the photon's absorbed, doesn't survive. If at the other end omega is 1, the photon is never absorbed, they all survive. And you'll see this guy again later on. Now, how do you measure the VSF? Well, if you think ACSs and such are complicated instruments, to measure the volume scattering function, you need to have an instrument that can shine a light on some little volume of water and then look at that volume from all different directions in order to get the whole volume scattering function. And the very first instruments, and most of them today, even in the laboratory, they maybe look from, let's say, here's our light source coming in, here's the little volume of water. Well, I can't put an instrument looking in exactly the backscatter direction because it would be blocking the beam. So maybe I can look from like a scattering angle of 170 degrees. And if I get out here, I'm looking straight into the beam and that burns out my instrument. So maybe I can look at a scattering angle of 5 degrees. So there's lots of ways you can figure out how to do that. We could teach that whole next week on optical engineering of volume scattering function meters, which is not worth your time, but there are a number of instruments around. There's some references here. Most of these instruments are one of a kind. They were developed by the scientists, used by them. They're not available. They're not commercial products. Sequoia Scientific now has a VSF instrument that is a commercial product. So if you're interested in it, take a look there. So here's some data now. This fellow, Ted Petzold, way back in the 70s and 80s, developed some instruments for measuring the volume scattering function. He actually had 2 instruments, one that worked down at a fraction of a degree, and the one that worked from 5, or maybe it was 10, to 170 degrees. And then he took the data from the 2 instruments and pieced them together to get a pretty complete volume scattering function. And then he went around and did this in various water bodies. And so here you see in the red curve, that's a turbid harbor, actually San Diego Harbor. It's got a high magnitude. There's coastal ocean that's off the coast of California. and clear open ocean, that was in the Bahamas. So this guy, if you integrate this curve, it has a scattering coefficient of about 0.04 per meter. This curve is about 1.8 per meter. And this is plotted now on a log-log scale, which really emphasizes the small scattering angles. Here's the same data plotted on a log linear scale. So you just see this very highly peaked scattering back here, but it shows you the mid-range of angles a little bit better. And so this Petzold data it's almost like become a law of physics now, but it was really a half a dozen data sets, and that's it. And they were perfectly good measurements for the water Petzold was in. But you should not expect Petzold's coastal ocean water, which was off the coast of California, to be the same as the coastal water that's 10 kilometers offshore here. Different particles, so on. Okay, so we've got the volume scattering function. If we integrate that, we get the scattering coefficient. That's just a number. So if we just divide this equation by B, well, that's B over B is 1, and beta over B is called the phase function. Has nothing to do with the phase of light, has nothing to do with the phase of the moon. It's just the name it was given. And the Russian literature tends to call it the scattering diagram, which is a much better name, but it hasn't caught on anywhere outside of Russia. So anyway, here's the definition. The scattering phase function is the VSF divided by the scattering coefficient. Now this guy tells you both the strength and the angular pattern of the scattered light. B tells you only the strength. So how much light is being scattered, how much power. And so the ratio gives you this guy, which only shows the angular dependence of the scattered light without any information about how strongly the light is scattered. So that's the idea there. To plot a few of these, here's the phase function. Now, we just looked at volume scattering functions, units of per meter per steradian. And if we look now at phase functions, they look the same shape, but now, of course, the units, we've divided out the per meter part with B. So phase functions have units of per steradian. They're how much is scattered into a solid angle per unit steradian. And so you usually see it plotted here, but here's a little 3D view where the white circle is the equator of the sphere. So that's scattering at 90 degrees. And then here's scattering at 0 degrees and then around to the backscatter directions. And then here's just this little green area here blown up for the first 10 degrees or so. So you see this plotted different ways, but here you see that it's azimuthally symmetric because we're not dealing with polarized light and we have randomly oriented particles. So that's just the way to plot things or to visualize what's going on. Now here's the idea. The volume scattering function is highly variable. And if we just look back, here, there's 2 orders of magnitude variability between Clearwater and Turbid Harbor just in his data. And of course, if you pick one of these curves, that's almost 10 to the 4th down to 10 to the -3 or so. There's sort of 6 orders of magnitude difference from between the small angles and the big angles, which is a horror show for building an instrument because you're getting a very bright signal up here and a very weak signal back here. But that's a story for the optical engineers to worry about. So anyway, the VSF is highly variable. The scattering coefficient is highly variable. But now the question is the ratio maybe not very variable? This is going to be determined by both what kinds of particles are there and their concentration. This is really determined just by what kinds of particles are there because we've normalized out the concentration effects. So that's why people like to play with this guy. Well, here's a bunch of data collected by Professor Voss. And this was off the coast of New Jersey. This was 530 nanometers. Here's a whole bunch of measured phase functions. And then the red curve is this Petzold average particle phase function. So you take all the Petzold's measurements, you subtract out pure water, and then you average what you have left, and people created this average particle phase function. Well, you can see on average, it's pretty good. It goes right down the middle of the data. So if you were making a volume scattering function on the day when it's one of these curves in here, it looks just like Petzold. So you could take Petzold, plug it into Hydrolite, you'll get great results. But if you were making a measurement on this day or on this day here, and you use Petzold to model that phase function, you're going to be off by a factor of 3 or 5. And then, of course, you'll blame it on Hydrolite, but I'm used to that. So keep in mind that when you have any kind of average whatever, it's probably good on average, but it might or might not be good for your particular water body on this particular day at this particular location. And once again, even though we're in the same water body, more or less, like right off the coast of New Jersey, there's an order of magnitude variability in the phase functions over the 3 or 4 days that these data were taken. Okay, so I pretty much said that you know, when you run a radiative transfer code, whether it's Monte Carlo or Hydrolite or whatever, you're going to have to put in information on absorption and scattering. Part of that information is the VSF or the phase function. The problem is you rarely ever have measurements of the VSF or the phase function because the instruments just aren't around. You'll have measurements on the absorbing and scattering coefficients. So then you end up saying, well, I don't know, I didn't measure the phase function. I'll just use Petzold and hope for the best. And that might or might not work. It's for sure the most common problem when you compare numerical predictions coming out of Hydrolite or a Monte Carlo code with what you measured in the ocean, let's say for remote sensing reflectance. They don't agree. It's almost always because you were putting the wrong IOPs into the numerical model. And we'll talk more about this later, and you'll see it in the Hydrolite labs next week. Okay, I want to say just a word about particle size distributions. The next lecture by Meg is going to be on particle size distributions, but basically they are a way of measuring how many particles there are of a particular size per unit size interval. And I'll leave it to her to go through the arithmetic, but basically if you have some measure of particle size, which could be like the diameter of an equivalent volume sphere or something like that, and you look at the particle concentration, so how many particles per cubic meter are there per nanometer or micrometer of size here, you get some distribution where you have a few big particles, more medium-sized particles, and lots of really small particles. And that function is called the particle size distribution. And Meg will tell you all about it. Now, why that's important is that scattering depends strongly on the particle size. You have lots of different sizes of particles in the water. So one water body has one size distribution, one has a different one. They'll have much different scattering properties. And here's a photo here. This airplane's flying along 1,200 kilometers an hour, 25 meters above the sea surface, which is right down here. And it's clear air here, and there's this like weird cloud thing going on here and a little bit here. What's happening there is if you think of a cubic meter of air right here, it's got a certain amount of water in it, but it's there as water vapor, as molecules. And the molecules are very weakly interacting with the light. They're small particles. They do a little bit of Rayleigh scattering, but not much. Now, this guy's flying supersonic. So there's a shock wave coming off the bow or the nose of the airplane. And when you go across the shock wave, there's a drop in pressure. So this cubic meter of air here crosses this shock wave. All of a sudden the pressure is less, which causes the water vapor to condense out and make fog. It's just like if you take a cubic meter of water here in this room and you lift it up far enough, it eventually cools and the pressure decreases and it turns into a cloud. So that's what's happening. So we have the same amount of water per cubic meter, let's say 1 gram per cubic meter, but here it's a relatively small number of big water droplets, and here it's a very large number of water molecules. So you've changed the size distribution, and these big water droplets scatter sunlight very strongly. So all of a sudden you see this white cloud, and then as the plane goes along and you get back out of the shock wave region, the pressure goes back to what it was, the cloud evaporates, it goes back to water molecules, and you don't see them anymore. So moral of the story is everything else is the same, but you just change the size of the particles, you radically change the scattering. Okay, here's a few more volume scattering functions. Here's Petzold's volume scattering functions for in the red curve here. Here's a model we'll talk about in a minute. And then here's Petzold versus some measured phase functions for little microbubbles in the water. And you see the microbubbles very strongly forward scattering. Then there's kind of a weird bump here at around 80 degrees or so, and it goes down, and then it goes back up by a factor of 2 or 3 or 5. So there's the Petzold. It doesn't really look much like the scattering by little bubbles, and bubbles meaning like, 10 or 100 micrometers in size, or maybe up to a millimeter. Here's some phase functions for oil droplets. The red is the average Petzold. These are oil droplets where they've been in the water for a day, a week, 2 weeks, or 5 weeks. And so what's going on here? It's the same oil or what? Well, of course, at 1 day after the oil spill, the composition of the little oil droplet, it has a lot of volatile sort of gasoline kind of molecules in it. They tend to evaporate out or leave. And so the composition of the particle changes and you get more of a thick tarry particle rather than a little fluid oil particle. And the particles tend to coalesce and they get bigger as time goes on. So there's, over an order of magnitude change in the forward scattering as these oil droplets age. And of course, even for a given day or a given age, there's almost an order of magnitude, at least a factor of 5, dependence on the wavelength because of the wavelength dependence of how the oil absorbs and scatters light. Here's typical atmospheric volume or phase functions here. And you notice, well, extremely highly scattering here. That's due to diffraction around the little water particle or ice particle, whatever it happens to be. This is water particles. So you get a big peak due to diffraction around the big water droplet. And then there's a funky little bump here, and there's another bump here. Well, this little bump is what's causing rainbows. That's, enhanced scattering compared to what's on this side versus this side. There's more scattering, it's wavelength dependent, et cetera, et cetera. And so this bump at about 140 something degrees, that's a rainbow, which if the sun's behind me and I'm looking this way, the rainbow's out at about 40 something degrees around. That's the angle from here to here. Well, 180 minus 40 is the 140 something here. If you look out at airplane windows, and I always get a window seat on an airplane so I can watch this stuff, you fly over clouds, you'll often see something like this, a ring of light around the shadow of the airplane. That's not a rainbow, it's what's called a glory, because it's a very small little region, but there's the little bump there at about 175 or so. That's the effect of this bump here on generating that little colored ring. Okay, here's ice crystals. Now, here the thin line coming down, and it's got this peak here and a peak here, and then some other peaks here. That's a computed phase function for hexagonal ice crystals. And you can go through like the side of the crystal, or you can go through the end of the crystal and come out the side, and those things deflect the light in slightly different directions. So you get a weird bump here, you get a weird bump here. Well, this bump at 22 degrees is what's causing this arc here. The bump at 46 degrees is causing this halo here. These other things are caused by not randomly oriented ice crystals doing weird things that are asymmetric scattering. But anyway, anytime you see something like these halos or rainbows or whatever, you know there's going to be a little bump in the shape of the phase function that's telling you what's going on there. Okay, so things to remember is that the volume scattering function, if we go back here, this very highly forward peak, that's really due to diffraction around the ice crystals. And then this is due to light that's going through the ice crystals or being reflected off the surface. Well, the volume scattering function parameterizes all of these very complicated interactions between light and a water droplet or the bubble or the crystal or whatever, and all the diffraction and reflection and refraction and all of that simply gets turned into the shape of the volume scattering function. So if you know the volume scattering function and you use that to model the light field, you can actually account for diffraction effects, but you don't actually have to do diffraction calculations. Okay, the magnitude of the VSF depends on the type and concentration of the particles. The shape of the VSF depends on things like particle size and shape and internal structure and index of refraction, but it doesn't depend on the concentration of the particles. And so everything you've seen here is for unpolarized light, and these things are, of course, always going to be dependent on wavelength. And now, so we kind of shift to the second half of the lecture is to talk about Iop models for scattering. And we'll run through water, phytoplankton, CDOM, non-algal particles, detritus, minerals, and take a quick look at these things. And then we'll screw all the pieces together and get some Iop models to use in hydrolite. So one question, Megan, you need a full hour, 45 minutes, hour and a half, what? Okay, so it's a quarter till now, actually 10 till almost. I may have to cut this a little short and somehow, you know, we'll finish it off after lunch or something. I don't quite know, but let's just carry on. The VSF and all the IOPs are additive. So the total absorption is absorption by water plus phytoplankton plus CDOM plus whatever else is there. Same thing for the volume scattering function. If I have the volume scattering function for water and for this phytoplankton and that phytoplankton and that non-algal particle, et cetera, I just add them all up and I get the total volume scattering function for the whole volume of water. Well, if I divide this by the scattering coefficient, this becomes the phase function, but the total scattering divided by the scattering coefficient for each component divided by the total gives me this ratio here, and then the phase function for that particular component. So VSFs are additive. Phase functions you can add together, but you have to weight them by the relative importance of each component and how it contributes to the total scattering. So what components make sense? Well, for computing the total, well, we'll have water, phytoplankton, colored particulate organic matter, colored particulate inorganic matter, bubbles, whatever else is there. Okay, for water, the red curve is the phase function for pure water. The green curve is a so-called Rayleigh phase function that you would use for the atmosphere, for example. They're not quite the same, and the reason is the Rayleigh phase function was developed for spherical particles. Water molecules are not really spherical. They've got an oxygen and a couple of hydrogens out here. So there's a little bit of correction. The atmospheric scattering by spherical particles or nearly spherical goes like 1 over wavelength to the 4th. Water is really like wavelength to the 1 over 4.32. The Rayleigh phase function is 1 plus cosine squared. The water phase function is about 1 plus 0.8 cosine squared. So there's little differences, but it's a Rayleigh-like scattering by water molecules. And then if we look at temperature dependence, you guys have already looked at that. So here's salinity. If we hold the temperature constant and you vary the salinity, you can actually get about a 30% difference in the scattering coefficient going from fresh water to very saline water at a given temperature. Or if we hold the salinity constant, so 35 PSU or parts per thousand, that's basically typical open ocean water. And as you vary the temperature from freezing up to very warm water, there's not much effect on the scattering coefficient. So you learn that absorption can be very strongly dependent on temperature at some wavelengths, but not on salinity. Scattering is strongly dependent, or at least moderately dependent on salinity, but not on temperature. Here's just some measured phytoplankton volume scattering functions, the dots, and in each case there he's plotted the Petzold San Diego Harbor volume scattering function. And you see that, well, you know, Petzold's not that bad until you remember, oh, this is a log plot. So there's like an order of magnitude almost between here and here, or between here and here. And yeah, Petzold does go down the middle, but you know, you can be way off if you were working with this phytoplankton and modeling it by Petzold. So if you haven't figured it out yet, it's a very important trick to know that if you have really crappy data, plot it on a log scale and it'll look really good. So instead of saying, gee, I have a factor of 5 difference in my VSFs here, well, plot it on a log scale and they look really close together. And you can then slip that past your examining committee. Okay, so models for scattering then, well, a very common model says, I want to know particle scattering, so I've subtracted out the water. So I've got particles and they look like the scattering coefficient at some wavelength and then a function of wavelength or whatever this normalizing wavelength is to some power n here. And n is typically taken anywhere from 0 to 1, just that kind of covers the broad range. So here's the wavelength dependence of the scattering coefficient for different values of n from 0 up to 1. And so people will use this kind of model just because they don't have any data. They just pull it out of the air and say, let's try this. Well, what do the real data look like? Okay, here's scattering coefficients in case 1 waters that is dominated by chlorophyll bearing phytoplankton. Here's case 2, so there's mineral particles and whatever else in there as well as phytoplankton, and it's normalized by the average value. Well, you see there's a dip here, and it's down, there's maybe another dip here, and it's kind of independent of wavelength, but clearly there's some wavelength dependence. And here's another set of data where they looked at various measurements, and the red curve is the lambda to the -1 dependence. Well, obviously that's too steep for any of these data. They're not really independent of wavelength, but they're not something like 1 over lambda either. So that's why you need to measure this stuff if you possibly can. Here's scattering by several different mineral particles, and here's scattering by non-algal particles. And these things, minerals in general tend to have higher scattering and absorption in the blue and lower in the red. And of course, high absorption in the blue takes out the blue light, and that's why the dirt looks brown or reddish or yellowish. It's kind of the same shape as scattering curves, but not necessarily. Non-algal particles you've already seen have these fairly nice sort of exponential shapes, but with a lot of variability. Okay, here's some measurements of backscatter coefficients and backscatter fractions. So people often say, okay, I know the scattering coefficient depends on wavelength and the backscattering coefficient depends on wavelength, but maybe the ratio is kind of independent of wavelength. So here's some plots of scattering. Let's see, yeah, these are all backscatter fractions. They're fairly close to being independent of wavelength, but not perfectly so. This is typical of the kind of numbers you get. Notice the backscatter fractions here. These are all in kind of the 1 to 2% range. These here are sort of 2 or 3% backscatter fraction values, just different water bodies. So what people often do is, rather than use that power law to model the scattering coefficient, they use it to model beam attenuation. And that gives you a better fit, the total beam attenuation, better fit to simple power law than the scattering itself. So they model the beam attenuation with the power law, and then they measure the scattering, let's say for non-algal particles or phytoplankton, and subtract that from the model beam attenuation to get the wavelength dependence of the non-algal particles or the phytoplankton. And this is usually fairly smoothly varying. This guy will have some bumps in it. So putting it all together then, if you want to model for the backscattering coefficient by particles, what people will do is model the backscatter fraction and often assume that's independent of wavelength. They'll model the beam attenuation and then they'll subtract out perhaps a model or measured absorption to get the scattering coefficient. Just a typical way things are done. And you'll have options when you run hydrolite, for example, to say, well, I measured this, I don't need to model it. Okay, life's good, put in your measurements, but I didn't measure it, so I have various ways to model it by picking these coefficients and so forth. Okay, here's more measurement of backscatter fractions by people who have taken data, fit curves through it, and come up with models as a function of chlorophyll. Well, here's 3 curves. You'll notice for, let's say, a chlorophyll of 9 or 10 out here, we're going from something like 0.004 up to 0.08 or 9. So a fraction of 2 or a factor of 2 difference for the same chlorophyll. Same thing back here, chlorophyll of 1, it's maybe 0.0075, and here it's 0.004 or something, a factor of 2. Well, what's going on there? It's different data sets, different water bodies, fitting curves through it, and seeing what they get. Here's the actual bunch of data. So chlorophyll versus backscatter fraction. The values are going from less than 0.5% up to over 4%. So here's this cloud of data. And if you fit these different models through it, you get these different curves. And these are just least squares best fits. Well, I gotta be honest with you guys. If you have a cloud of data like this, don't waste your time trying to fit a curve through it. Just say, you give me the chlorophyll of 1 and I might have 0.5%, or I might have 4%. So as I said the other day, scattering does not correlate well with chlorophyll, because the reason this particle's low and this one's average and this one's big is they have different sizes, different shapes, you know, whatever's going on inside, and they all might have the same chlorophyll, but much different sizes and shapes. Okay, so here's just more models, backscattering fraction for phytoplankton and non-algal particles. And you can see ranges of 0.5% up to 6%. Depends on your water body and which day you're out there. There are a lot of analytical models for phase functions. I'm only going to mention one, which is this thing called the Fournier-Ferrand. We see the black curve here, which is the average Petzold, and the red curve does a pretty darn good job of matching the black curve, whereas these other models that people have cooked up over the years often are way off at small angles and way off at the big angles. Okay, there's this fellow, Georges Fournier, who has more brain power than everybody in this room put together, me included. He did this horrendous amount of math, starting with me theory, which we'll learn about later. And he was able to analytically sum up the me calculations for all particle sizes from 0 to infinity, but really for just the range of ocean particles. And he comes up with this really weird looking nasty equation, which is the Fournier-Ferrand phase function. And what goes into it is we have the particle size distribution, and that has some slope, which he calls mu here. And then it's got, the particles have some index of refraction n. So if you give me the slope of the size distribution, in this case, n is -4 for the black line, but it could be this slope or it could be this slope. Give me the slope of the size distribution, give me the index of refraction of the particles. That determines these things. And I then plug these quantities back in here, and there's our scattering angle. And I get this big, nasty formula. And, you know, Fournier goes to this oceanography conference one time, lays all this math on us. And I thought, well, yeah, so what? But, you know, I got home, I programmed it up, and holy cow, it really works very well. So you can actually, if you want to amuse yourself, take this equation and integrate it over psi equals pi over 2 to pi, and you can get the backscatter fraction, and you'll eventually get this formula. And so in hydrolite, you'll have an option that says, use a backscatter fraction of 2% or 3% or 0.5% or whatever, and a Fournier-Ferrand phase function. So what it'll do is it will go get one of these Fournier-Ferrand phase functions that has that backscatter fraction, and it'll use it. And that can range from, you know, phytoplankton down here at 0.5% up to mineral particles, maybe 1.2%, and it goes back and forth along these lines. And here's the Petzold average particle phase function, which has a backscatter fraction of 1.83%. It's right there. Okay, there's a whole family of these things built into hydrolite, so you pick the backscatter fraction, it'll go get the appropriate phase function. And here's this data from a manual again, with Petzold in the middle. But if I pick these few of these curves that have different backscatter fractions, so the blue curve here is measured, it was green up here. So here's high backscatter fraction down to low, and the red curves are the Fournier-Ferrand phase functions with those backscatter fractions. And they do pretty well out to about 160 or 70 degrees. And then the measured Fournier-Ferrand tends to go back up, whereas the measured one goes back up, whereas the Fournier-Ferrand tends to level out. So things can be off by a factor of 2 or 3 or whatever here, even if over the rest of the range, it's very good. Let's see. It's now 5 after 11. How about I stop now, turn it over to you. What's on the agenda for labs this afternoon?
Scattering.
Scattering at what time?
We typically start at 1:30.
Okay,
We could do,
I'm,
have like 15 minutes more.
I'm close to done
So
here.
let's finish it up at 1. Why don't we lunch from
Yeah,
until 1, and then you can finish up, and then we can go to the lab at 1:30.
yeah, okay, so after Megan, lunch 12 to 1 here, we'll finish up a few more view graphs, another 10 or whatever. And I don't want to
Sounds
cheat
good.
Megan out of her time, so.
Excellent. Cool.
While she's setting up,
So I think because our morning sessions are taking an hour, which is really useful time, I think we should plan on starting maybe at 8 rather than 8:30. So that will give us enough time in the mornings for you guys to present your stuff, take a little break, then we'll start with the lecture. Does that seem okay?
yeah, we had a long session. Since the annual told you his story, about medical problems, I'll tell you mine. So, in January, I was walking across my yard, not doing anything stupid. There was a little sloping section of grass. And I stepped on the little sloping section. And of course, the grass is wet because it's raining. And my left foot slipped out in front of me, but my right foot